Hello, everyone. I hope you're doing well and staying safe and healthy. We now start with Module 6, in which we're going to be learning about how to manipulate chemical equilibria in ways that may produce a different sort of outcome for us. So with this, we're going to first talk about equilibrium constants and conditions in this module. Our learning goals today are how can we manipulate the equilibrium of a chemical reaction? What are the different ways that we can do that? And what happens when we put two chemical equilibria in the same mixture? It turns out that this also has a great influence on the position of chemical equilibria, and it's a situation that actually occurs probably more often than not in nature. We already know there's lots of different ways that we can change equilibrium states. We learned this from Le Chatelier's principle back in Module 4. Among those ways, we could add a reaction species. So, for example, if we added a reactant to a chemical reaction that's at equilibrium, the response would be to try and deplete some of the reactant that we've added, so it would push the reaction toward products. On the other hand, if we'd added a product, it would push the reaction back toward reactants. In other words, the change always opposes, the shift always opposes the change that we make in a chemical reaction. The opposite of adding a reactant or product is to remove one from a reaction. That way we can cause the reaction to replenish that thing that we've removed. So if we remove a reactant from a chemical reaction at equilibrium, it would shift toward reactants in order to replace that reactant that we removed. We also know that under Le Chatelier's principle we could change the temperature of a reaction, and in that sense the reaction will always move toward one side or the other based on what the enthalpy change or the heat change is in the reaction. So we can treat heat as though it is one of the reaction species. So for example, in endothermic reaction we would add heat as a reactant, so if we raise the temperature it would push the reaction toward products in order to remove the heat that we've added by increasing the temperature. We also know that we can change the volume, and this will affect, for example, gas phase reactions, because if we increase the volume, making all of the pressures lower, the reaction will respond in order to add more gas particles to the mixture, and so it opposes the change by increasing the pressure again. The same thing would happen with diluting a reaction mixture. That really works the same as increasing the volume of a gaseous reaction. Now, one of the effects that we're going to be very interested in is something called the common ion effect. It basically is a situation in which we're going to have an ionic species, typically in an aqueous solution, and by having one of those species in abundance, or by adding some to that solution, we can shift the reaction according to the Le Chatelier's principle. Now, maybe the simplest case to think about is a solubility equilibrium, which is shown here on this slide. Let's suppose we just have some generic ionic compound, I'll call it MXN, and we know that when this dissolves in water, it's an electrolyte solution or a partial electrolyte solution, so it's going to form some metal ions and also some X- ions, and we'll say there's N of them. The solubility product constant, which is the equilibrium for this reaction, is simply the product of the concentration of the metal and the concentration of the anion raised to the N power. Now, if we were to add some metal ions to this mixture, the equilibrium would shift to the left and more solid compound is going to be formed. In other words, we're going to be pushing some of the X- ion out of solution. On the other hand, if during the course of dissolving this in an aqueous solution we removed one of those ions, the equilibrium would have to shift back to the right and more of our compound would dissolve in the solution. So already we can see a very handy way that we could shift the equilibrium of a solution, shift the equilibrium of a solubility of something in the solution. Now, one of the other ways that we're going to find is very useful for changing equilibrium systems is by having multiple equilibria present. Now, this doesn't automatically change the situation for us. Those two equilibria have to be coupled together. Now, what does that mean? What does coupled together mean? It basically means that they share a reaction species in common. So if two equilibria, for example, both have hydronium ion present as part of their equilibria, then the two equilibria are influenced by one another because they both affect the concentration of the hydronium ion. Now, the best analogy I can come up for this, and it's a little bit hokey, but imagine two people that are sitting on a seesaw, and they can find an equilibrium point, that is a point at which the two of them would be stably sitting without rocking up and down, and it's more or less based on how far they are from the center of the center of the seesaw and how heavy they are. Okay, but imagine if you had a weird playground where you had seesaws so close together that the same person could sit on two different seesaws, and there would be partners on both of those seesaws helping them to balance. Well, that would be a very complicated balancing situation. I think you could imagine it would be pretty difficult to find the right conditions that would allow you to sit stably in one position. But that's nevertheless, that situation could exist, and that in some sense represents what we're finding when we have two coupled equilibria in the same reaction mixture. Now, in order to figure out what the effect is going to be for this, we need to have ways of combining the equilibrium constants when we have two different species together, two different reactions together in the same mixture. So, for example, if we have two reactions, reaction 1 and reaction 2, and they each have an equilibrium constant, which I'm calling in this slide K1 and K2, what I'm interested in is when I add the two reactions together, what is the resulting equilibrium constant going to be? All right, and I've drawn this out as two acid dissociation equilibria, one for hydrogen fluoride and one for nitrous acid. And so both of them produce hydronium ion, and both of them produce their corresponding conjugate base, the anion that goes with the hydrogen ion. Now, it turns out when we draw out the net reaction, we add the two reactions together, so that would be the long reaction shown below that. That's HF plus HNO2 plus 2 waters goes to form 2 hydronium ions plus fluoride ion plus the nitrite ion. All right, if we were to simply write the equilibrium expression for that new compound reaction, we would get the equilibrium constant that's at the lower right. But we can see how this is related to the two equilibrium constants for the reactions we added together. Those are shown to the left of that, K1 and K2. They're drawn out explicitly as the concentrations of the reaction species. We can see that K1 plus 2 is actually just the product of the two reaction equilibria constants for the two reactions that were added together. So this is generally true. If we add two reactions together, two equilibria, and we want to know the equilibrium constant for the sum of those reactions, it's going to be the product of the two equilibrium constants of the reactions that add up to the net reaction. Now, what happens if we reverse a reaction? So let's suppose we take that hydrogen fluoride acid dissociation equilibrium, and I'll just call it equilibrium constant K now, and I just reverse the reaction. So I say I'm going to put fluoride ions in with some hydronium ions, and they're going to come into equilibrium with water and undissociated HF. Well, when I reverse that reaction, I basically turn the equilibrium constant expression upside down. So the reverse chemical equilibrium, K reverse, is just the acid dissociation equilibrium, but upside down. So it's equal to 1 over K. And this is going to be generally true also. Whenever you reverse the direction of a reaction, you basically take its equilibrium constant and do 1 over that equilibrium constant to get the net equilibrium for the new reverse reaction. We also need to know what happens if we multiply an equation by a certain constant, say A equals 3, what happens to the equilibrium constant in this situation. So once again, we have the hydrogen fluoride acid dissociation equilibrium with chemical equilibrium constant K, and we're now going to multiply that equation by 3. And it's fairly easy to figure out what that does with the chemical equilibrium constant expression. We're going to have basically all of the 3 concentrations raised to the 3rd power. So when we work that out, It turns out that the new equilibrium constant is just going to be the same as the old equilibrium constant, but now raised to the third power. And again, this is a generally true situation. If we were to multiply by any constant, a, or whatever you want a to be, the resulting equilibrium will be the old equilibrium constant raised to the power of the number that you multiplied by the entire reaction. Now, a last thing that I need to, concept that I need to cover is the issue of a dominant equilibrium. That's an equilibrium that is, in essence, going to shape how all of the other equilibria respond to it. All right, so it is, in some sense, dominating the equilibrium mixture. Now, my analogy, going back to the seesaws, is what if one of the characters that's balancing the seesaw with you in the middle happens to be really heavy? Okay, well, that is going to form a dominant equilibrium. That person's going to be tipping the seesaw way up, affecting where, what height you sit, and that's going to affect the person at the other end of the seesaw on the right-hand side, who is much less heavy than the dominant equilibrium. All right, so in this way, chemical reactions can also dominate an equilibrium mixture and cause it to sit in a certain place relative to others. Now, what usually causes this? It often is caused by a great difference in magnitude of the equilibrium constants. So best example I can say is, once again, using our hydrogen fluoride example, the acid dissociation. If we simply write out HF plus H2O goes to fluoride minus plus hydronium ion, that has a Ka of 6.76 times 10 to the minus 4. Now we know in every aqueous solution there is another equilibrium present. It is the water autoionization equilibrium, and I've written that out. 2H2O goes to hydroxide ion and hydronium ion. But the Kw for the water autoionization reaction is 1 times 10 to the minus 14. It's much, much smaller than the other one. So in fact, what tends to happen is the weak acid dissociation dominates the equilibrium, and it's the thing that really sets how much hydronium ion you're going to have in the mixture. The one time this won't be the case is if the concentration of your acid, your weak acid, is very low, and so it doesn't produce as much hydronium ion. If it produces the amount of hydronium ion that's close to what you would get in pure water, then both reactions are more or less of the same dominance, if you will, in that reaction mixture. Now, the typical protocol that we're going to have for solving for this with dominant equilibria is we are going to first solve the weak acid dissociation, assuming that it's dominant. And when we do that, we'll find the expected concentration of the hydronium ion. Now, as I said, if that hydronium ion is in between, say, 10 to the minus 8 and 10 to the minus 6 molar, that's very close to what we would get in a regular pure water solution, where the hydronium ion would be 10 to the minus 7 molar, then it's a case where we're going to have to solve both of the equilibria together. We're going to have to use some more complicated techniques to solve it. But if the hydronium ion that we get from the weak acid dissociation is much larger or much smaller than this range of 10 to the minus 6 to 10 to the minus 8, then we can use that to basically set the initial equilibrium value of the hydronium ion, and then let the water autoionization reflect that hydronium ion concentration. So let's consider this example again, where I've got hydrogen fluoride autodissociating in water to form fluoride ion and hydronium ion, and the water autoionization equilibrium. So the concentrations that we're going to need in this case would involve, these are the ones we have to solve for in order to solve the complex multiple equilibrium problem, would be the concentration of the undissociated hydrogen fluoride, the concentration of the fluoride ion, F-, the concentration of the hydronium ion, H3O+, and the concentration of the hydroxide ion, OH-. Okay, so those are the four concentrations that are in that solution, and we need to find out what they are when we combine these two equilibria together. Now, I'll point out that this is kind of like solving an algebra problem that has four variables. Now, your head is probably shrieking right now, my God, I don't want to be solving an algebra problem with four variables. How can I do that? Well, believe it or not, it can be done. what I'll point out, though, is that anytime you have a mathematical problem with four variables, you need at least four equations that relate those variables to one another in order to have a unique solution. So in this case, we have four concentrations that we need to know. We would need to have four conditions that relate those concentrations to one another. Now, two of those are going to be the equilibrium conditions that we already have for those two chemical reactions. So the first one being the acid dissociation constant for the hydrofluoric acid. That relates the three concentrations to a constant. And the other is the water autoionization equilibrium constant, 10 to the minus 14, which relates the hydronium ion and the hydroxide ion. So four concentrations are unknown. We have two conditions that link them. So that means we need two more conditions to hold them together. Two of the ones that often are utilized in this case would be mass balance. Now, let me explain what that means. In mass balance, we're saying basically all of the fluoride that's in the solution has to come from the original hydrogen fluoride. There's no fluoride in pure water. So that means that the initial concentration of the hydrogen fluoride acid that I put in, HF with a subscript 0, has to be equal to the equilibrium concentration of the HF plus the equilibrium concentration of the F minus. In other words, the stuff that's on the right-hand side contains all the fluoride that's in the solution at the end of equilibrium. The thing on the left-hand side is all the fluoride that's in the solution before anything has happened. Now, we also have a condition that requires charge balance. And I hope this is something that you can relate to, but if not, I'll try to explain it. The stuff that we put together at the beginning has no net charge. That is, there's no net positive charge, no net negative charge. Everything is neutral. But we know that both of these reactions, as they move toward completion, as they move toward equilibrium, they produce ions in the solution. Well, we can't produce more positive ions than we have negative ions. So in effect, the charge balance tells us that the total concentration of the positive ions in the solution, which is all hydronium ions at this point, has got to be equal to the combined concentrations, the sum of the concentrations of the fluoride ion and the hydroxide ion. And only this way will we have a net neutral solution. In other words, it won't have any net charge. So it's just saying all the positive charges in the solution have to equal the same magnitude as all the negative charges in the solution. So now we can apply this if we were to, for example, ask what is the pH of a 10 to the minus 8 molar solution of nitric acid? Now, let me step away for a second and just say, if we were just seeing this for the first time, our first impulse would probably be to say, okay, the concentration of nitric acid is 10 to the minus 8 molar. I know nitric acid is a strong acid, so it completely dissociates when it goes into water. So that means that the concentration of the hydronium ion that's produced is 10 to the minus 8 molar. Okay, well that's great. Now I'm going to go calculate what the pH is. Okay, well, as we learned in Module 5, the pH is just the negative of the exponent for the concentration of the hydronium ion. So if the concentration of the hydronium ion is 10 to the minus 8 molar, that means the pH would logically be 8. But now think about that. When we think of a pH of 8, that's above pH 7, which is neutral. Any pHs that are above 7 represent basic solutions, not acidic solutions. So the conundrum here is that we have added an acid to water and we've ended up with a solution that's actually got a basic pH. Well, that can't happen. So what's wrong? Well, the thing that's wrong is that we did not include the autoionization of water when considering what the concentration of hydronium ions would be in this solution. So once again, I'm writing out the two equilibria, the nitric acid dissociation in HNO3 plus H2O forming nitrate ions and hydronium ions. And we know that that acid dissociation constant is really large. So we're going to, effectively, it's going to be complete. And then we also have the water autoionization equilibrium, which we've been talking about with Kw of 10 to the minus 14. Okay, just as we had in the HF case, we've got four unknown concentrations, nitrate, nitric acid, nitrate, hydronium ion, and hydroxide ion. So now we want to see, are there other conditions we can impose? Well, we're going to assume that all the HNO3 dissociates when we do this. So that means there's no undissociated nitric acid left in the solution, and that's actually a pretty good assumption. So the nitrate ion that we get out of that has to be equal to the initial concentration of the nitric acid, and that was given as 10 to the minus 8 molar. Okay, that's the only place the nitrate can come from. Okay, it doesn't come from water, doesn't come from anything else. All we have in the solution are nitric acid and water. So all of the nitrate had to come from the nitric acid that dissociated. So we've already solved for that concentration. Now let's look at the water equilibrium. So we've got the equilibrium constant is equal to the product of the hydronium ion and the hydroxide ion is equal to 10 to the minus 14. If we do charge balance, remember that we have to include the nitrate ion now because it's producing negative charge in the solution. So it's, in some sense, it's going to influence then the amount of H3O plus and OH minus that are produced there. And we know that that nitrate ion is equal to 10 to the minus 8 molar. So in fact, the total concentration of hydronium ion in the solution has to equal to 1 times 10 to the minus 8 plus the amount of hydroxide ion. So H3O plus equals 10 to the minus 8 plus OH minus. So now we're gonna create an algebra problem. Sorry about that. We're going to let X equal the hydroxide ion concentration. So now when I write the equilibrium expression for Kw, and this is now toward the bottom of this slide, I'm going to write Kw is equal to the concentration of hydroxide ion times the concentration of hydronium ion. And now I can plug in values that are in terms of X for both of those concentrations. The hydroxide ion is X, and the hydronium ion is going to simply be the hydroxide ion plus 10 to the minus 8, so that's 1 times 10 to the minus 8 plus X. And that product has to be equal to the equilibrium constant for water autoionization, or Kw. Well, we can solve this. It's, if you don't like solving things by hand, you can always plug it into Wolfram Alpha to get it. I'm not going to go through that detail here, but what we find is that the value for X is 9.5 times 10 to the minus 8. Now notice 9.5 is very close to 10. So what that tells us is that the hydroxide ion concentration is very, very close to 10 to the minus 7. It's a little bit smaller than 10 to the minus 7. All right, which tells us that there is less hydroxide in the solution than there is hydronium ion in the solution. So now when we find the hydronium ion concentration, that's going to be 10 to the minus 8 plus the 9.5 times 10 to the minus 8, which gives us 1.05 times 10 to the minus 7 molar. All right, now these are small numbers, and I want you to be sensitive to the fact that 1 times 10 to the minus 7 molar is a neutral water solution. 1.05 in the hydronium ion concentration, 1.05 times 10 to the minus 7 is a very slightly acidic solution. And indeed, when we take the negative log of that number, we get a pH of 6.98. Okay, so when we see this answer, it should reassure us that adding an acid, even in a very, very low concentration, adding an acid to a pure water solution will produce a slightly acidic pH. So, have we learned something about manipulating the equilibrium of a chemical reaction? I hope so. I hope you have a good feel now that this can be done either through techniques using Le Chatelier's principle or through techniques of having multiple equilibria. We've also seen what happens when we have two chemical equilibria present in a reaction, and this is something that makes it a little bit more complicated to solve, but nevertheless gives us a chance to figure out what the equilibrium concentrations are going to be for all the species in that mixture. Thank you.